share my screen again. Okay, so no, wrong screen, I think. Okay, can you see the screen?
Yes.
Yeah. Okay.
But it's yeah. Can you maximize full screen?
All right. So zoom in a little more. Yeah. So here, this is it's a small demonstration for an optimization search space. So what I have written here is, in general, the ideas that were presented in the presentation, that the transfer learning is advantageous in these two transfer learning scenarios where the search space is expanding, and in the case where the search space is the same but the problem becomes more complex. So here, transfer learning for this actually function comes under the first scenario where the search space is expanding. So the actually function is something that is familiar to most of us who are looking at optimization problems. So this is basically a search space are basically defined by this function where x is the input space and the function is a nonlinear function that is defined with these summation terms, where this series term sigma I equals to 1 to d, this defines the number of parameters that we are optimizing on, right? So to start off with, we do the optimization on a small size problem where we fix the d to 2 dimensions, and then we apply transfer learning for a larger size problem where the dimensionality is like 5, right? And this can be arbitrarily increased, but we chose these values so that it's easier for us to demonstrate. Oh, then this is the usual. You can see the notebook. This is the usual for loading DeepHyper. Yeah, and this is the definition of the actually function that I showed before. And here, this is the run function that is used to wrap the actually function. This is what I was calling. So we can typically call black box functions through this wrapper, where the input is the dict, which defines the search space, and the output is the objective function, right? And we define the small problem with 2 parameters. 2 parameters, and large with 5.
Sandeep, will you be able to execute, because this would be fast, right? So this notebook is fast.
Yes,
so
I can.
Will you be able to execute? Yeah, thanks.
Let's do it. Okay, now let's.
So everyone can execute this, because this is easy to use or computationally cheap.
Yes.
So if you have access to Colab, please go ahead and run them.
Now we are inputting DeepHyper. This is the problem definition. Now we are defining a smaller search problem which has two uh, two dimensions, and here is the range that we are choosing for that. Then we define the 5-dimensional problem. Here we initialize the centralized Bayesian optimization with Gaussian process surrogate. In this case, because both the parameters are this search space is continuous, and it's a relatively smaller problem, so the Gaussian process surrogate model works better. So that's why we have used this, but it can be easily changed to a random forest. We set the number of valuations to be 100. So this bar, this fancy bar, shows the progress as the evaluations are being done. And remember that here we are not doing a parallel run across multiple workers, but the same code can be currently adopted to run on large clusters, right? In the next talk, I think they'll touch upon how to scale this or run across multiple GPUs. Yeah. So this is taking some time, but we're almost done. Yeah, feel free to ask questions and if you run into any issues while running this notebook. Now, the search on this two-dimensional space is done. We have got 100 evaluations, and the best objective is this value. And now we run on 5-dimensional space. And by the way, the objective should be close to 0. That's the global optimum. So once we have this search done, we can look into how this search space is, and then look at transfer learning. I'll show you how simple it is to enable transfer learning. Thanks to Roma for making this API very easy to work with. Yeah, while this is running, if anyone else has any other questions, feel free to ask.
Sandeep, I have a question, if that's okay. Uh,
Dennis.
I'm just curious, how far have you gone in terms of extending the search space? So now you're showing an example of D of 2 to dimension of 5,
Yeah.
right? So that's almost like doubling the search space, or a little more than that. Like, how far can you go, and at what point is your previous knowledge kind of becomes useless, or is it really problem dependent?
Yeah, I would say it is much more problem dependent. So in the example that we showed in the slides, right? So we went from 11 to 20, 20 parameters. But I would think, in theory, it should be applicable, uh, but nothing would stop if we increase the number of parameters, right? So because I think what generative model is doing here is biasing the search on what we have in the past. If the maybe if the parameters are too many, it the what we say the advantages of using this bias search might go down. It might take more time to converge. Yeah.
So Nasar, in that case, I think, let's say, you have only 2 parameters in the first task, and then you go to 100 parameters, right? So now you have to deal with 98 parameters for which you don't have any knowledge. And in that
Exactly.
case, yeah, you could eventually bias those 2 parameters, but the impact will be much less profound compared to, let's say, 5 or 10. So that's, in that, if you have 100 parameters, then, doing the search from scratch,
You should search from scratch.
yeah,
Yeah.
that's better. But of course, you can bias those 2 parameters, but the impact would not be as good as, something that you have seen in the presentation or here.
One thing you could also see is like maybe like if you have like 100 parameters, you can select different subsets.
Yeah.
And perform separate searches on them and then combine them. And that's also one good way to parallelize it as well, I think.
That's right. Correct. So that's a more domain decomposition way to do that. And in fact, the categorical parameters are a lot more amenable to do that, to split that and sort of do it in a separate. But one thing to note that there is, there are certain combination of categorical parameters that will be like poor, and you can easily identify them in the very beginning. So it's either you have to kill that search and restart with something else, or you have to be a little bit smart about changing the fixed parameter space or fixed partition from the beginning. So the partition should be a lot more adaptive. That's the point that I'm trying to make.
Yeah. And this could be really powerful. Thanks.
All right, so the search is complete here. You see, when we just ran on the large search space, it converges around the objective value of 20. And next, this is the change that we need to do transfer learning. So we define the problem as we did before, but the only change is we are going to fit a generative model, and here it shows a quantile value of 0.8, which means that we are picking 20% of the high performing configurations. And now doing the search is already biasing it based on this generative model. And you can see with around 80 evaluations, it has gone to an objective value of 0.001, whereas earlier it was around 20. So you can clearly see that transfer learning is helping get to better objective values quicker. So like this function can be adopted for other hyperparameter search problems that were defined, or the notebook that were shown earlier this morning. So the only difference is we need to select which parameters that we want to, or how do we want to bias the generative model. In this case, the results of small is a file of that has the configurations that are evaluated for the smaller search problem. So this is the file. It needs the file of the configurations and the quantile value, and rest all will happens in the background. Right. So once we have this, you can see there is a huge difference between doing a direct large problem versus doing a transfer learning on this larger problem from the smaller problem. Right. So you can see even the configuration objective of the best configuration is much lower, and also you see the time or the number of evaluations it takes to get to this is also much lower. Yeah, that's pretty much what we have in this notebook. Yeah, so I think this is the key, that you can take this and experiment with other hyperparameter search problems that you are looking at. Let us know if you have any questions.